Okay, guys, now I think we're at a point now that we can discuss or look at another type or another class of functions which we're going to deal with in our course. In this case, we're talking exponential functions. I just assume that you don't know what an exponential function is, if I know that some of you have got some idea of what it is. But my idea is to try to get you to understanding a bit what it is all about. In a way that you understand that mathematics is not just about taking symbols and playing with them somehow. These things have got some use in life. This is what I always try to do. If there's an example which I can use in reality to make sense of some piece of mathematics, I'll use it. But like I said the other day, it's not always possible to have some practical example of all mathematics. Because some mathematics just for the purpose of mathematics itself, but some things you can apply. Now, let's start with a simple story like this one. This is about life. I'm taking it from biology. You know, what is the simplest living organism or organism, maybe, a cell, né? It's a cell. A cell is an animal or it's something more or less like this. There's got a cover there, membrane. There's got some liquid there called cytoplasm, and then I've got a nucleus, which is actually maybe the core of it all. So now, cells produce themselves, but there's no mother cell, there's no father cell. Now the cell multiplies itself. If nothing happens to kill it, you will just have a cell producing and increasing population. So what happens? The biology theory says this nucleus grows to a certain size. Once it has grown to a certain size, it breaks into two. I remember in biology, my biology teacher did something like this. He ended up with a nucleus which looks more or less like this. And somewhere it breaks into two and produces two cells. So now, if we start the experiment this way, this is day 1. Or let's say day 0. 0 day 1 meaning the initial time when we start the experiment. Let's say now day 0. Let's say day 0 is first day. So if this cell life cycle takes 1 day, which means after 1 day, we have grown, fully grown and divided into 2, isn't it? So then, after 1 day, we're going to have 2 cells. Now this one is divided into this. So that is after 1 day. Then following day, now it's after 2 days. This cell would have produced something there, and this one would have produced something there. So I'm now drawing this roughly. I hope you understand what I'm saying. Then the following day, this one will go, this one will go there, this one will go there, this one will go there. We're talking about an ideal situation where we're in a lab and these things are protected from any type of accident. So we're guaranteed that on the 3rd day, we're going to have this number of cells. Okay. Now, somebody can now guess on the 4th day, how many cells are going to have? 16. On the 4th day, we're going to have 16. Actually, here what we have, we've got 8. Is that so? Here we've got what? 4. Here we've got what? 2. And here we've got what? 1. But you see here, these numbers which are here, maybe 1 is not obvious, but these numbers which are here, they are obviously powers of 2. Isn't it? So then we end up having something like, if we number these days using n, say n days, if you look at this here, after 1 day is 2, which is 2 to the power 1. And after 2 days is 4, which is 2 to the power 4. So now the population of these cells after n days is going to be 2 to the power n. altogether. And that is somehow our first experience of what is an exponential function. And the other thing which you must take from here is actually maybe some kind of a partial answer. What is mathematics? What is mathematics? I mean, you are engineers, but what is mathematics? For you as an engineer, what is mathematics? I think for me, mathematics is a language for which I can communicate science, engineering, and the technology. How was I going to say this in English? To tell people how the population of cells multiplies and the changes around today. How am I going to say this in English? I need to say it in mathematics and give the formula and say the population after n days is going to be 2 to the power n. But when you say it in English, 2 to the power n, write a sentence. The population of cells after n days is 2 to the power n. It doesn't mean anything. Then you need this mathematical expression for that. So for me, I think for you also, you must try to see that mathematics is a language for which you can communicate in science, engineering, and technology. Maybe English, Afrikaans, Zulu, whatever, it just becomes tools to just just aid the communication. Otherwise, it's this final expression that I'm going to have a function now which is called f of x, y is equal to f of x. Now, I might not necessarily be dealing with 2. I might be dealing with any number a to the power x. Then what do I have there? Then I've got what I call an exponential function. Am I making myself clear? Now, I suppose that now everybody knows how an animal called the exponential function looks like, isn't it? So now we're going to now look at its properties, check a number of things, then we know exactly what is involved. In this case here, I will always assume that my a is greater than 0. And my a equals to 1 is not interesting. Altogether. So I'm not going to include it there. Why is it not interesting? Because it's the linear function, a line, a constant. It's going to be 1, 1, 1, 1, it's a constant. So I'm not really interested in putting it there. So what I'm going to do now, we're going to deal with a less than 1 greater than 0 in one case. In the other case, we're going to deal with the a greater than 1. Then what we're going to analyze actually is to analyze what are the properties of these functions when we've got these different conditions. Altogether. Now, but I think first of all, let's start with this base 2 and try to draw the graph and see whether it can make sense and maybe deduce what other graphs would also look like if we do not necessarily have 2. Altogether. Okay. So, in other words, now I'm saying we're going to look at the function f of x is equal to, in this case, I'm going to use n. I'm going to say f of n is equal to 2 to the power n, but I want to take those discrete values like 0, 1, 2, then we go on. Altogether. Now, let's clean up this a bit. Then we say here, f of n equals to 2 to the power n. Now, let me call this, let me just graphing exponential functions. So I've got an example here which is f of n 2 to the power n. Now let me draw a system of x's. And then this is n equal to 0, isn't it? So we're dealing with n here, like n1, n is equal to 0. Now, on day 0, when we start the experiment, how many cells do we have? 1, isn't it? 1. We are actually saying that 2 to the power 0 is equals to 1. I'm still going to come and talk about this thing of power 0, which is very interesting. Maybe let's just talk about it now. Let's just solve this thing. Don't say this thing like any number to the power 0 is equal to 1. It's not true. Any number to the power 0 is not equal to 1. It's not true. You throw away that confusion today. What is true is 2 divided by 2 is equals to 1, isn't it? And any number divided by itself is equal to 1. That is true, isn't it? But if you go back to the rules of exponent, this is 2 power 1 and this is 2 power 1, isn't it? Then this is equals to 2, according to the rules of exponent, is going to be a minus b. You see that? And that is 2 to the power 0. So the reason that 2 to the power 0 is equal to 1 is not because any number to the power 0 is equal to 1. It's not true. 0 is a number, isn't it? 0 is a number, isn't it? But 0 to the power 0 is not a number. Okay, so good. Let's go. Let's move away from that. But be careful when we say those things. Then there's 1, there's 2, there is 3, there is 4. Let's stop there. Now, at day 1, at day 0, there's 1 cell. Day 2, day 1, there's 2 to the power 1, and with 2 cells. So we're somewhere there. First day we're there. And day 2, we had 2, 3, 4 cells. So day 2 was somewhere there. How do you Do you see what I'm saying? Okay. At day 3 with 8 cells. Let's say maybe we can continue there. It will maybe somewhere there. And we continue. Now let's try to attempt to extend this thing to the negative side. This will be minus 1. Now which means this will be half. Then you have 2, you have not half now, it's minus 1. Then you have 2 to the power minus 1. But what is 2 to the power minus 1? It's 1 over 2. Which means if this function continues, extend this domain this side, then we're going to have half there. Below 1. When you get to minus 2, we are going to have 2 to the power minus 2. Then we got a quarter, which means there it's going to be even less. You see that? So one property now we're seeing about this function, exponential function, that as we go to the left, it decreases. As you go to the right, it increases. Altogether. So that is the graph of the exponential function. And it cuts the y-axis at 1. It's clear, isn't it? Now, listen to me. Can you stop writing a bit and listen? Now, here I'm dealing with the whole integers. I started with natural numbers, whole numbers, 0, 1, 2. Then I extended to integers, minus 1, minus 2, and you can see what happened, isn't it? Now, what is interesting now is that if we deal with intervals, like all the numbers in between there, we're going to have those filling that thing there. Those filling that thing there. I understand what I'm saying. So at the end of the day, we're going to have a graph smooth graph becoming difficult like that. So that graph becomes a graph of an exponential function. Then now the solid graph now, the dots are f to the power n. The solid graph is f of x equals to 2 to the power x, and you call that an exponential function. Are we together, guys? Are we together? Okay. So, I think it's clear also here that 2 is greater than 1. Sorry, 2 is greater than 1. Remember I said, we're not going to be interested in a being equals to 2. We said generally, the exponential function is going to be x, f of x equals to a to the power x. We said a is equal to 1 is not interesting. Now we said we're going to deal with a between 0 and what? 1. Because 0 also is not going to be interesting. Isn't it? So, but we now stick to this region and that. So now we're dealing, this 2 is giving us a there. Then the question which is interesting is that how would the graph of a here look like? Now talking about 2, I think the most important a we can think about now is 1 over 2, isn't it? Do you agree with me? 1 over 2. Let's say now we've got I now want to discuss with you briefly, I want to discuss with you when the base is a number less than 1. So in this case I'm saying, let's suggest to deal with f of n equals to 1/2 to the power n. Again, now n, I'm going to take an integer from minus what? Minus infinity to infinity. But let's just start at minus 2 or minus 3. Let's start at minus 3. Minus 3. Minus 3 here. What's going to happen here? If we say f, now that's where comes now the evaluation of a function. Remember the evaluation function. We need to use that. F at minus 3. This will say half at minus 3. Elsewhere, what is that? That is 8. So which means at here it's going to take this value 8 which you take here. It's going to be 8, isn't it? So maybe let's clean a bit there so that we can put our 8. Let's clean a bit there so we can put our 8. Our 8 is at that level according to that graph. So above 3 here, we're going to have another 8 there. Then let's go to minus 2. What are we going to have for minus 2? Minus what are we going to have? 4. So which means that one there is going to be somewhere there, 4. And then minus 1, 2. What do you see happening to the function? Is it growing or is it increasing? Decreasing. At 0, 1. How do it? 0 equals 1. So it comes there. At 1, half. It will come here. At 2, quarter. Now let's take another color there. I think let's get this reddish color. And now, if we now consider the same thing we did there, we would have fill the gaps here, fill the gaps here, and go down. Okay. Then we have a function which goes this way. A graph of function which goes this way. Sorry, I'm missing it there. That's that. And then we've got two functions now. We can see on the picture what happens when a is greater than 1, what happens when a is less than 1. This side, the first one we discussed, is an exponential function. what we call this growth. Now it's an exponential growth. Right there is I'm just writing the growth for exponential growth. All together. And this exponential growth, as you come from infinity, that's the values are very small, but we never expect them to be zero. Now, the red one we call it decay. That's the graph which describes how we are using our natural resources. They are not increasing. What are they doing? They are bit by bit getting depleted. But the population of people is increasing. And then this is how the population is increasing exponentially, and this is how the natural resources are decreasing. Then you can think about what you hear on the TV. Conservation, conservation, conservation. Can you describe this mathematically? Yes, here it is. What is mathematics? A language to communicate in science, engineering, and technology. And also a mathematics, a science of its own. Altogether, mathematics is like a chameleon. If you take it to engineering, it's something else. If you take the mathematics, it's something else. Because there's also mathematics for the mathematics itself. Altogether. Okay. I think it's beautiful. Huh? It's beautiful. I mean, a chameleon is beautiful because it changes color. That's how mathematics is also beautiful. Okay. So guys, I think here I've made you have a feel of what an exponential function behaves like. Indeed. So now I think we're ready to kind of write a summary. Now not talking about 2.5, but talking about the A in general. Altogether. Okay. So let's do that. So I'm saying exponential functions. Am I too slow or am I too fast? I'm too fast. I'm in between, so I'm fine. Okay, it's okay. Thank you for that. Right. So the animal we're talking about, or the mathematical object we're talking about, is something like this. Now, I'll also, at this point, try to comment on the transformations. Those transformations like vertical shift, horizontal shift. So if I've got a exponential function like this, to incorporate that thing you already discussed, so I've got a exponential function like this, x minus, let me just say x minus k, h, plus k. I want to emphasize, exactly like I wrote the equation of parabola, I want to emphasize the similarity of what's going to happen. I hope I did say to you before, in the parabola where it's x minus x, h squared, I said this h talks about horizontal translation, isn't it? And the k talks about vertical, k, vertical translation. Altogether, if it was for me, I would write vertical with a k, so that it adjusts to my mathematics here. But so not to avoid annoying a lot of people, I will leave it like that. But you must understand yourself that that is that. So what I'm trying to say there, having already a picture of a graph of an exponential function. So when you get an exponential function in this form, you must try to kind of figure out what's going to happen. Okay. But this is not what I want to discuss now. What I want to discuss now are these special cases. Let's say case, no. Let me not say anything case. I'll just go on there. Let's say point number 1, initial point, 0. When A is greater than 1, we know that this is going to be growth. I'm just summarizing what it is, isn't it? Now, point number 1, when A is between 1 and 0, we say this is going to be decay. And we know when you talk that saying this is a decay, when people don't see the graph, we must picture the graph in our head. How to get it? Decay. Then what else? Then point number 2, what is important? The intercept. The intercept on y is at y equals to 1. I'm talking about the standard function like this without the translation, isn't it? Then, what is also important, the asymptote. Asymptote. I don't know if I'm going to spell this correctly. Is that correct? Asymptote. As is S-A-S-Y-M-T-O-T-E. The asymptote is horizontal. What is this equation? X, no, is it X? Y, it's Y, isn't it? Y equals to 0, which is the x-axis, isn't it? The x-axis. Listen here, we're discussing the basic function, or the very, very first version of function, which is the first one there. Then, once you've got a general form of it like this, we'll then incorporate the horizontal translation and the vertical translation altogether. Okay. So, I think that's what I'm going to highlight now. The rest, please go in the check in your book, and we'll go further with that. Are we right, guys? Are we right? Okay. So, talking about these exponential functions is also important now to remember the rules of exponents. Altogether, let's remember the rules of exponents, because somehow manipulating exponential function will involve the rules of exponents. Let me say there, just to revise a bit, let's say rules of exponents. First of all, we've got a to the power x. If I'm not mistaken, this is called the base. Altogether. And that is called, what is that? The exponent. Exponent, or the power. Altogether. The exponent. Then, I've already explained this. First of all, we know that a to the power x multiplied by a to the power a, what's that going to give us? A to the power x plus y. Then we've got a to the power x divided by a to the power y. Then that becomes a to the power x minus y. Then we know a to the power x divided by a to the power x. Then we know that this is a to the power x, a to the power x minus x, which gives us what? A to the power 0. But this is from a to the power x divided by a to the power x. What is that? 1. Altogether, it's not anything to the power 0 equals to 1. Alright, so then after that, we notice that 1 divided by x to the power n is the same thing as x. Now, what am I doing now? I'm trying to say I'm trying to say 1 over a to the power x is equal to a to the power 0 over a to the power x. Isn't it? It's true, isn't it? Then this is what? A to the power 0 minus x, and then we've got a to the power minus x. I think we used this thing when we were graphing our power half, or half to the power n. Okay. Then the other thing which is actually also important in terms of this, I'll just go to it, is that x to the power half multiplied by x to the power half is equals to x to the power half plus half equals to x to the power 1, which is actually equals to x. If you multiply a number by itself and get a number, like we multiply 2 by 2, you get 4. What do you say 4 is? Is the square of 2, isn't it? Yes or no? And what do you say 2 is? What is 2 or 4? Square root, is it? Huh? Yes or no? If you multiply 2 by 2, what do you get? 4. What do you say 4 is of 2? 4 is the square root of 2.
No. 4 is the root of 2.
4 is the root of 2.
No. But
4 is the square.
The square root of 2. It's a square.
4 is the square of 2. Listen to me. I'm detecting that you can't talk these things for yourself. You cannot tell yourself. Square 4 is the square of 2. What about 2? Square root of 4. Isn't it? Look at this thing here at the bottom here. You multiply x to the power half by x to the power half, you get x. So what is x to the power half of x? X is the square of x to the power half, isn't it? Let's say this is 2. 2 times 2, 4. 4 is the square of 2, isn't it? Now, what is 2 of 4? What is 2 of 4? Square root, isn't it? So, x to the power half is the square root of x. What I'm trying to remind you of there is that these powers, when they are rational, you can actually change them to roots. Altogether, go and check that. It's also going to be important. We're going to use that in our course. Otherwise, I'm going to stop there for a while in as far as exponential functions are concerned, and expect you to go into your textbook and play around with anything which involves exponential functions. Check the concepts we talked about before, the domain, the range, and I think we also talked about the inverse. We must start thinking about what is the inverse of an exponential function. That is what we're going to do next. Otherwise, thank you for now. Thank you for listening.